Hello everyone, welcome to another exciting session of Quantum Grad Talk series. Today we are honored to have Dr. Yaroslav Duda with us. Let me introduce him briefly. Dr. Duda has PhD degrees in computer science and physics. He is currently working at the Institute of Computer Science at Jagiellonian University. He is known as founder of Asymmetric Neural System or ANS. His research interests include two-way quantum computing, multidimensional joint distribution neural networks, and particle models as liquid crystal-like topological excitations. Today, he will be talking about two-way quantum computing. Particularly, he will shed light on how this architecture of quantum computing increases quantum supremacy and allows us to solve, in theory, NP problems and also allows better error correction. So, Dr. Duda, thank you so much for accepting our invitation. And if you are ready, the floor is yours.
Yes, thank you very much for this possibility. So I would like to talk about two-way quantum computers. So in standard one-way quantum computer, like here, we start with state preparation, then we have some unitary evolution, then we perform measurement. So in two-way quantum computer, we add this symmetric version of this state preparation. So we believe that physics is CPT symmetric. So if we can prepare state, then maybe we can also reverse kind of this process. So perform a process which from perspective of this symmetry is the original state preparation process, and perform kind of postparation, like preparation, but at the end. So I will show a few ways how to try to realize it. And if possible, and if successful, this possibility would bring better stability, error correction, and interior allows to solve and be complete problem. So this is essential improvement, not confirmed, but very promising. Okay, so we would have to think about quantum computation this way: that we have initial state, unitary evolution, and then there is the final state. So we can also project from the second side, and from CPT symmetry, there are reverse. So this is very popular notation, for example, for scattering matrix. So one approach to reach it is, for example, for silicon quantum dots, where the state preparation is performed by impulse of electric field to tunnel electrons to the dots. So performing a reverse impulse at the end, we would from CPT perspective, we would get the original state preparation. Yeah. So looking backward in time, we would get state preparation here, and then we would reverse this process. Yeah. So this is one approach, that if the state preparation is performed by impulse of electromagnetic field, then we can just use a reverse impulse to get process which from CPT perspective is the original state preparation process. So it should act as this preparation from the end. So we can evolve this situation also back in time, starting with state preparation here. So let's look at another example. So in superconducting quantum computers, there is, and many others, there is used very low temperature to like 30 millikelvin or lower to be certain that nearly all qubits are in the ground state. Yes, but from CPT perspective, temperature is the same. It's just mean energy. So it doesn't matter if you use it here or here. Yeah. So for example, looking at this situation, so we can start with the ground state as thanks to very low temperature and evolve toward right. But CPT symmetry allows us also to evolve backward. So we can take a look ground state here and evolve here. So symmetry of physics allow us to evolve both forward, starting from ground state here, but also backward, where this qubit should behave the same as this qubit. Yeah. So it starts with the low temperature, so it is nearly certainly the ground state. So we should be able to evolve it toward both directions. So a basic approach could be, for superconducting quantum computers, could be just avoiding the measurement, readout, which is a very invasive process. So thus not performing the readout and going straight to the reservoir or low temperature, evolving it backward in time, we would get then the original state preparation and going into the unitary evolution. So another example of realization is based on this similarity between hydrodynamics and electrodynamics. So they are governed by very similar equations, especially if having a superfluid which has no viscosity. So we are usually thinking about optical heating with lasers, but there is also optical cooling. We are thinking about pushing, but there is also cooling. There are tweezers. And finally, there is radiation pressure, which is a vector. It can be toward positive, toward the surface, but can be also negative, outward the surface. So having we can think about electronic chip situation this way, that we have this two-way control. So we have battery which both pushes electrons into the chip, but also actively pulls electrons from the chip with potential. So it has better flow better control flow of information thanks to that. Similarly, we can think about a microfluidic situation. So we have a pump which pushes fluid with positive pressure into the chip, but also actively pulls with negative pressure from the other direction. So, for example, they are starting to consider superfluid quantum computers. So, having them just connecting with pump into a loop like here, you will get two-way quantum computer. So then you have hydrodynamic situation, and there is a similarity between hydrodynamics and electrodynamics. In theory, we should be able to also do it with microwaves. And finally, the most practical would be doing it with photons. So, but we need analogy of pump for photons, and the ring laser seems to work like that, because in ring laser we enforce circulation of photons like here. So in this situation, we inject the photons toward them into the photonic chip. So what is used for state preparation. But looking at it from CPT perspective, we reverse the photon trajectory, so we should inject the photons from the opposite direction. So like for the dynamic situation, we both push into and pulse from, because from CPT perspective, we reverse the direction of flow. So this is another approach with photonic photons. I will talk more later about. So and I have started with the silicon quantum dots like here. So if there is just electromagnetic impulse like here with qubits encoded as position, then we can just reverse this impulse, and from CPT perspective, you get the original state preparation process. So there are also the other ways, like this Elzerman readout, which allows only for spin up to tunnel, or spin out are stopped. But again, there are all of them are controlled by electromagnetic impulses, so we can just reverse the shape inside the controller to get something what is from CPT perspective is the original state preparation process. Another approach for silicon quantum dots is using strong magnet to enforce, let's say, spin up. So usually it is applied before for state preparation, but if we apply it after, again, we enforce spin to be up at the end. So evolving backward in time, we would start with spin up. So I don't see any reason why not to use it after for CPT analog of state preparation. Okay, so we had some team for X Prize. We had quantum interns program. There are a few articles. So generally, we need help to try to, especially to realize it on real quantum computers. Maybe to develop into the photonic approach, or silicon quantum dot, or superconducting approach. So we are looking for a collaboration to help with that. So let me go to this logical algorithmic part now. So how to think about these two-way quantum computers? So it is basically a one-way quantum computer, but post-selection, but with higher success rate. So because post-selection does not always work, we need to ask for this condition until it is satisfied. So there is some probability that this condition is satisfied, and in two-way quantum computer, it should be nearly always satisfied. So let's think about quantum computation. So it leads to this finally, before the measurement, we have some density matrix, including some noise imperfections on the go. Then in standard one-way quantum computer, you just measure everything using this standard formula. In post-selected one-way quantum computer, we would add some more qubits, let's say m qubits, and measure all of them, but discard all which does not satisfy the condition. So the probability is like here in numerator, like above previously, because we measure all of n plus m qubits. However, we discard all of those which are not condition. So we need to divide by probability of that this condition is satisfied. So this is standard post-selection one-way quantum computer formula. So the problem with this approach is that the probability of this condition being satisfied often drops exponentially with the number of qubits you would like to post-select on. Yeah, so having 10 qubits, it's like 1 divided by 2 to the power 10. So that's a big problem that we need to make many runs until we get the condition satisfied. So in two-way quantum computer, with this density matrix, we would make this projection first, and then we would measure the first qubits. So doing so, the formula would be the same as for selected one-way quantum computer. However, the improvement is that the success rate, instead of being exponentially small, now it should be close to 1. So optimistically, we should get exponential speed up in comparison to standard post-selected one-way quantum computer. Yeah, so for example, to solve NP problems, I will talk in a moment about, and that it is very similar to Aronson post-BQP complexity class, also adding post-selection, and it is known to contain NP. So it is basically known that we would be able to solve NP problems with post-selection. However, two-way quantum computers in theory allows to replace this post-selection of low success rate with something of nearly complete, nearly always successful. So that's the advantage. Okay, so let's think about this solving NP problems, some more practical. So the Aronson is quite abstract, and then let's think about a practical way to solve NP problems, assuming we have this postparation, post-selection. So here is some approach. So in NP problems, it is given by a polynomial time verifier. So in polynomial time, we can check if given input is correct or not. But the difficulty is that the number of inputs is exponentially large in practice. Yes, like for the 3-sat problem. But we have the verifier is that checking if all the alternatives are right. So we have alternatives of triples, and some variables can be negated. And the question is, could we find the values so that all these alternatives are true? So this is example of an NP-complete problem. So if being able to find polynomial time algorithm to solve this problem, you'll be able to solve all NP-complete problems. So this is a very nice problem to work with. So how to solve it with such having such postparation? So we can prepare state, use Hadamard's to prepare superposition, and then ask, for example, about these alternatives. Yeah, so this is the alternatives with nodes as in 3-sat problem. So now the standard way would be to measure them, and for example, in Shor algorithm. Instead, in two-way quantum computer, we can enforce them literally, so or perform post-selection. So performing post-selection, the probability of success would drop exponentially with the number of clauses we would like to enforce. In two-way quantum computer, we should increase this probability to nearly to 1. So enforcing them to 1, this verifier has to be satisfied. So the alternative has to be true ideally. So measuring these ordinal qubits, we should be able to find a solution which satisfies this NP problem. So this is the approach. So this is quite similar to Shor approach, Shor algorithm. So in Shor also we prepare quantum superposition of exponential number of inputs. Then we calculate classical function, this one. Then we measure them, and this measurement restricts the ensemble to periodic one. And with quantum Fourier transform, we can find this period, what gives us hint for a factorization problem. In 3-sat, instead of measurement, here we enforced one, post-select, post-pair to 1. And doing so, we should get a solution to this our NP problem, which we can measure. So if successful, So the consequences would be very large. For example, from one side, cipher breaking. So it would be much more powerful to break also standard symmetric encryption. For example, we can think about we can have a beginning of a file and try to encrypt it with the various keys. So using wrong key, we'll get a noise. Using correct key, you'll get, for example, lower entropy. So the verifier here would ask if with given key, encryption of the beginning of the file has lower entropy. Yes, and this way we can think about it as problems. In theory, could be attacked with for example, two-way quantum computer maybe. So this brings the question: could we find design better post-quantum cryptography, which could be resistant to NP solvers, quantum NP solvers like two-way quantum computers? But from the other side, there is also global optimizers, then applications, better applications. So like, for example, for the drug design, so we could, for having global optimizer, so with a problem, we can think about, we can ask if there is value for which this function is below some threshold. So this way we can get a global optimizer with NP solver. So for example, we would like to find a molecule which is perfect for given function. So the best drug for given evaluation. So for example, for drug design and many other optimization problems, it will be very valuable. Also, I mentioned that two-way quantum computers allow for better stability, error correction, thanks to this two-way control of information flow through our quantum chip. Okay, so this was a theoretical possibility, but in practice, obviously, we don't have perfect quantum gates preparation and so on. So the question is, what happens for not perfect two-way quantum computer? So a perfect quantum computer would prepare density matrix having only the solution to our NP problem. Imperfect one, here is some model, would also have inputs which break some of the clauses. Yeah, so let's say epsilon to power 0 would be that all the clauses are satisfied. These alternatives. Epsilon to one clause is not satisfied. Epsilon square, two clauses are not satisfied, and so on. So the problem is that this number grows exponentially. So for practical and solvers, we might need to reduce this epsilon down to like 2 to minus n. So it is very restricted. The question is, could we do it with error correction? That's a difficult question. However, so for example, working with many copies, in theory, we should be able to arbitrarily reduce this epsilon. So that there is a hope. Also, two-way quantum computers allows for better error correction. For example, here is some basic gadget. So this gadget in standard one-way quantum computer for error correction, we would measure here. But here in two-way quantum computer, we can enforce this qubit to 0, and doing so, we literally enforce the two qubits to be 0, to be equal. Yes, so having this gadget, this new gadget only allows for two-way quantum computer, we could work on multiple copies of the same qubit. So this way we could make some, for example, work on serial given qubit, or maybe work on multiple copies by using this equalizer. So there are many ways to improve stability, error correction, thanks to two-way quantum computers. So it's quite promising to faster get to quantum superiority. Okay, so another approach is through Groover algorithm. So the standard one requires square root of the number of possibilities. But for two-way quantum computer, this article by Grzegorz Czelusta has shown that we can get down to constant time. So it's huge improvement. So here is such circuit. So here will be standard measurement, and instead in two-way quantum computer you can enforce it to 1. Thanks of that, he claims that we get to nearly constant time, and then also noise dependence is much better. So for example, here is the blue line is the two-way quantum computer, and the remaining are for standard one-way quantum computer, and we can see that the noise dependence is much better for two-way quantum computer. Yeah, so literally thanks to two-way control of the flow of information through our chip, we get better stability of the calculations. So this is another improvement over the standard quantum computers. Another question we can ask is, could we validate the no-cloning theorem with two-way quantum computers? But this is very similar question to could we do it with post-selection? Because mathematically they are practically the same, but this is improved version of postparation is improved version of post-selection, and we cannot. So we have shown it in this article. So that there is the standard approach. So that we assume that there is this cloning operator. The extension is that the standard would end here. We would have just A and B qubits. Here we also have these additional qubits which are prepared somehow and finally projected to post-selected, post-paired to. So assuming that there exists such cloning operator for two-way quantum computers or post-selected one computer, and using it for the basis, we can show the contradiction that it would have to satisfy these equations. Also cannot be true for cannot clone all the states. Okay, so one slide about these possible consequences. So the current post-quantum cryptography is focused on the Shor and Groover algorithm. So I think it's not very responsible because there could be better algorithms, there could be better improved algorithms like two-way quantum computer. So I think it would be safer to at least search for better post-quantum cryptography. So the question, so some next-gen post-quantum cryptography, which could be resistant, for example, for quantum solver. I think this might be approachable in the future, for example, with two-way quantum computer. So the question is, are current post-quantum cryptography resistant? I'm not certain. So NP hard is not sufficient if you have NP problem, NP solver. So the question is how to build cryptography which is resistant for hypothetical quantum NP solver. So one approach could be to require initialization because so based on cryptographic key, we need to make some calculation, and then after this calculation, you can perform the decryption. So this way, the superposition, as mentioned, would have to include this calculation, and this can be costly. So we cannot maintain a superposition for this cost. Yeah, so this is one direction to try to exploit the weaknesses of quantum computers superposition. And another direction might be based on higher complexity class like p-space. So there are a few p-space problems. For example, a three-sat problem with this for all quantifier, or the reconfiguration problem that we need to search for a path of values which satisfy some constraints. So I have made something similar in this prep in the past. Another direction could be some pathless games. So there will be literally multiple interactions to decrypt. So we could attack one interaction, but there are multiple dependent interactions. So you cannot put it into quantum computer, for example. Okay, so the last part discusses further about physics, maybe photonics, quantum computers mostly. So physics is believed to be governed by, to be satisfied in CPT symmetry. Yeah, so that means that looking at physics from perspective of CPT symmetry that evolving backward in time, the equation should be the same. So this CPT symmetry has time reversal, the most important, and usually sufficient. For example, for electromagnetism, we can only think about time, but also parity and change of charge to the opposite one. So, and there is this Schwinger CPT theorem that Lorentz invariant quantum field theory, local, with Hermitian Hamiltonian must have CPT symmetry. Yeah, so they are drawing these Feynman diagrams, and the opposite diagrams also need to exist with antiparticles kind of traveling backward in time. So it's called Feynman-Stackenberg interpretation. And if violating CPT symmetry, it would be really bad. So we would have to rewrite the fundamental physics. And the proposed approaches might show it. So they might not work because it might turn out that while microscopically the CPT symmetry is right, what was confirmed in many experiments maybe macroscopically there is some violation. So we can also find this kind of violation, which could prevent quantum computers and different possible applications I will also mention. So one could ask, what about second law of thermodynamics? So we have symmetry, CPT symmetry, which says that past and future are very similar. And from the other side, we have entropy growth, which is not symmetric. Yeah. So are they in conflicts? So they don't have to be in conflict because there can be symmetry in equations, which is violated in solution. For example, this lake surface. In equations, it's symmetric, but in solution, just throwing a rock, the solution is not symmetric. Yeah? So this is not a problem to violate symmetry on the solution level. So, for example, for us, for entropy growth, we can think about, I think, about Big Bang as this rock, because everything was localized, so entropy was low, so it has created entropy gradient. We observe a second law of thermodynamics. But generally, so the question is how to think about time. So the intuition suggests this presentism, so-called philosophy of time, that we have the current moment and it evolves for all time. However, modern physics and CPT symmetry requires different philosophy. It's called eternalist block universe. That we live in four-dimensional solution like space-time shape, and just the current moment is in equilibrium between past and future. Yeah, so we literally kind of four-dimensional jello, which optimizes action, for example, in every point. So yes, kind of four-dimensional jello. Particles are the trajectories. We can show a Born rule in this view that literally there is amplitude going from one ensemble from future, ensemble from past, and we need to multiply both to get the probabilities as in Born rule. And having Born rule, we can have Bell variation. And this is, for example, the scattering matrix I have mentioned and used for two-way quantum computers, that we have literally the boundary condition doesn't have to be in one direction, but they can be symmetric. And between them, there is unitary evolution, which can be represented by unitary. They can be also used Feynman diagrams here. Yeah, so for example, quantum field theory using Feynman ensembles, it uses eternalities, it assumes ensemble of four-dimensional scenarios. Before general relativity uses one for this scenario, the space-time shape. So the modern physics requires eternalist block universe philosophy of time, which is CPT symmetry, in contrast to our intuition, which is not compatible with the modern physics. So this is crucial to use this symmetric view of time, especially for two-way quantum computers, that we have literally boundary condition in both directions, and based on them, we have Feynman ensembles between them, for example. Okay, so very nice CPT symmetry phenomena. Also at heart of most of quantum computer, I think, applications is the Rabi cycle. Yeah, so we have, for example, a laser and some atoms, and there are couplet oscillators. Yeah, so they are cyclically exchanging energy as photons. So and simple mechanical model is the just couplet pendula, which are cyclically replacing photons. Yeah, so using these two equations for lasers, the absorption and simulated emission equations, and thinking about this couplet pendula. So for example, for two-way quantum computer, you would like to put this unitary evolution of our chip kind of between these couplet pendula. Yeah, so that they exchange these photons through our quantum chip. Yeah, so having such multiple oscillators, and between them there is coupled between them there is our chip. In theory would allow for two-way quantum computer. Okay, so this is one view as couplet resonators. We can also think about laser kind of as this fan, which could both excite and de-excite these pendula or pendulums. Yeah, so we could imagine a fan to excite or de-excite a resonator, like a pendulum. Another view could be through hydrodynamics, that we have the water tank and there is a semi-transparent wall. So there is a standing wave, and the standing wave exchanges and pressure with this particle. Yes, it both pushes and pulls. Yes, so this particle should go over these oscillations by using positive negative pressure. Yeah, so this is crucial that we have not only positive pressure but also negative pressure. So we don't think about it about in electromagnetism, but it should be also there, negative pressure, radiation pressure. Okay, so to get Rabi cycle with lasers, we could naively should do it directly like here. However, I have checked literature and they don't do it. So I suspect that the problem is that usually lasers have built-in optical isolator. So it blocks the violet, the paths of photons from target toward laser. So if you block it, there is some problem. And looking for articles, I have found two ways that they go around this problem. So one was this paper which adds resonator. So we can think that the laser pumps the resonator and the Rabi cycle is between this resonator and our target, our atoms, for example. That second approach I have seen is this Mach-Zehnder-like. So you can see that here that literally that photons go one path here, but go back this path. Yeah. So and from CPT perspective, it's reversed. Yeah. So there is this problem of this optical isolator, but it could be we can go around it with some tricks. Okay. So now I'd like to talk about the most promising way to get this CPT analog of shooting with photons, and synchrotron radiation is the safest approach, I would say. So if this doesn't work, I don't know how to save CPT symmetry. Yeah. So I talk about but it's not very practical. I think, for example, the ring laser could be more practical, but this is ultimate approach. CPT symmetry say that it should work. Yeah, so in synchrotron radiation, we have, let's say, a charge going on circle, and it creates a photon. Yeah, but there is also CPT analog of this synchrotron radiation. It's called synchrotron self-absorption or self-amplified spontaneous emission. So, for example, like in this diagram from this link, one electron creates photons, which is absorbed by a second electron. But from CPT perspective, we reverse this trajectory of this electron, and this electron creates photon, which is absorbed by this photon, by this electron. So we shouldn't think about one causes second, but we can also reverse this causation. So yeah, so it is not this presenting philosophy of time is not correct here. Instead, you should think about this eternalis block universe philosophy of time. There is a Feynman diagram with this coupling of two electrons. That's all. It can be switched. It doesn't matter which causes which. Yes, so going to more practical realization, there are, for example, synchrotron, which have electrons going in circles. So standard view is this photon. So this photon so this photon is created by electron, and it absorbs the target, but also causes stimulated emission, like here. However, looking from CPT perspective on this diagram, we reverse this photon electron trajectory. So we should create this photon. Yes. So the question is, so it also is required on this original picture. Yeah. So we should have not only this view, but also this view. Yeah. So because this photon after this symmetry becomes this photon. Yeah. So the standard view that we have only this excitation seems not complete. There is missing also the second causation. We've reversed the order of these two electrons. Yeah. So we have again electrons circulating here in the synchrotron and electrons in orbital of atoms inside the target. Yeah. So the question is which is coupled. So they are coupled, but the question is what is the direction of this coupling? Can be this way, but can be also opposite. So CPT symmetry says that both are true, but everybody's focused only on the standard one. So I believe the second one is also very interesting and should have many applications like to quantum computers. So the question is so why we don't observe the second one. So for example, it is well known from astrophysics that there is like here is very nice Crab nebula with 20 orders of magnitude difference of the spectrum width. So usually the synchrotron radiation electrons would go in spiral, would radiate energy like here, produce this energy and lose this energy. This electron loses this energy going in spiral. So this is clearly not CPT symmetric picture, yeah. So it only emits photons because for the absorption it would need the source of the photons. So this is usually missing, that there is no source. So there is, as mentioned with the entropy growth, there is asymmetry in solution. That there is also that it is easy to produce photons, but it's difficult to get photons from the outside. But imagining that it is happening, for example, here with this noise, or let's say this cosmic microwave background. So this way, it could both emit and absorb photons. So this balance, energy balance, should be different because there should be both emission of photons, but also absorption, self-absorption of photons. Yeah, so generally it was, I have found one article considers CPT symmetry of synchrotron emission to be tested, this one, but generally so there is this Feynman diagram which have this photon emission and absorption, and it can be switched, so we can reverse in theory. And there is let's say the Compton scattering reverse one where electron absorbs and emits photons. So the question is, so let's think about this synchrotron radiation from CPT perspective. So here is standard synchrotron radiation. We have charged particle going on circular, let's say magnetic field. It produces photons, and these photons cause excitation of the target. Now looking at it from the T-symmetry perspective, we reverse this charge trajectory. So we should produce these photons. So these photons should excite target, but toward our negative time, because this is in T perspective, T-symmetry perspective. So in our perspective, these photons have standard trajectory, are absorbed by this electron, and cause de-excitation. Yeah. So these photons cause excitation of our target, but there should be also these photons which cause de-excitation of our target in the opposite direction. So however, we don't see them usually because they need that the target was initially excited. So this is very difficult to satisfy condition. Usually it's not satisfied, but could be, for example, satisfied by some noise, by thermal noise, let's say, or a different type of noise like electromagnetic radiation. Or we could artificially excite our target. So this equation is required. This is required by CPT symmetry, that we can also cause the excitation of target, but it needs that we have the target prepared as excited. So we have two equations. So standard radiation acts with this equation, this absorption equation of the target, and there should be CPT symmetry requires also this simulated emission equation of the target. And from CPT perspective, we would switch the two equations. And in Rabi cycle, we have both, for example. And for example, antenna can be seen as low energy limit, and it can both emit photons but also absorb photons. Yeah, so if you can emit, CPT symmetry requires that you can also absorb. And finally, so here is some hydrodynamical analog. So the question is how to imagine. So I mentioned that there is mathematical analogy between hydrodynamics and electrodynamics. So the question is what to think about photons. And for example, this wheel-like wave behind marine propellers carries energy, momentum, and angular momentum, like optical photons. There is no quantization, but there is very similar to our photons. And if it hits a resonator, it could both excite this resonator or de-excite this resonator. Yeah. So if we reverse the direction of this marine propeller, it should pull with negative pressure. For example, it could pull energy from this excited resonator. Yeah, so we can not only excite with photon sources, but then should be also these reverse photon sources, which allows to de-excite the target. Like in this synchrotron radiation, that we have both this positive radiation pressure, but also in fluid, if we create positive pressure, then we also have to create negative pressure from the other side. Yeah, so we can also create this negative radiation pressure. So yes, like here, so that we just switch the two electrons or the couplet resonators. So I'll be brief to talk about some other potential applications. So one could be a new type of telescope camera. So standard camera is focused on this positive radiation pressure. Yeah. So that the photons going from the pulsar cause excitation of in our sensor, and we monitor this sensor. We can say where these photons come from. But from CPT perspective, these photons should cause de-excitation of our target, like this wave, quiz-like wave. So we could observe it if having prepared target as excited. Yeah. So we need to use pump detector, also monitoring its population, and we should be able to see this synchrotron radiation, for example, but not thermal radiation. So we could, in theory, should get different type of camera which sees synchrotron but not thermal radiation. Yeah. So in both these two pictures, we have coupling of electrons, electron in the pulsar, let's say, and electron in atom in our sensor. Also here, but we just switch the direction in this Fermat diagram. Yes, we just switch them. Okay, so this is another approach, some new type of telescope we could build based on these considerations. And I have two more slides about some other applications of such this negative radiation pressure source. So, for example, we have these computer tomography scanners, which measure absorption coefficients of, let's say, some human body. Yes, so we have a source of photons. There is let's say the body of human body, and there is the detector for which we cool detectors where we monitor population. So this absorption subtracts the number of ground state atoms on the go. Yeah, so now we can see this integral of the ground state atoms on the go. But from CPT perspective, we would reverse the photon trajectory. And we'd have to excite, as mentioned, this detector as in this previous slide. So, and now we should be able to measure the emission coefficient. So integral of the excited number of excited star target on the go. Yes, so by having this negative radiation source and this reversed camera, kind of. So why is better? Because the number of ground state atoms is usually much larger than of excited atoms. So it should have much better transparency. Yeah. So while light goes like 1 centimeters per body, it might be 10 centimeters, 20 centimeters, maybe 100. So it brings a chance to scan human body in visual spectrum. So it would be much safer, non-ionizing radiation, and also multispectral, because there are many molecules which are excited by the chemistry. They are called autoluminescent molecules. So we could make multicolors 3D maps of these molecules, of various molecules, and so this is very promising for new medical scanners. and related application could be causing the excitation. Yeah, so like in two-way quantum computer, one laser causes excitation, the second causes de-excitation, and the opposite in CPT perspective. So like here, standard synchrotron radiation causes excitation, but there should be also this CPT analog which causes de-excitation. So kind of this twist-like wave when we pull, not push but pull with negative pressure. So we literally pull energy from excited resonators on the go. So the standard pushing is subtracted by the ground state atoms, but this pulling should be absorbed by the excited atoms. So but it's usually much lower number, so there should be better transparency. Yeah. So thanks of that, we could, for example, cause the excitation of, let's say, of NADH molecule in body. So it is responsible for the metabolism. So if you would cause the excitation like here, we could start the tissue, locally start the tissue. So it sounds very promising thanks to transparency for a better radiotherapy. Yeah. So we could point multiple such negative radiation pressure sources like here and try to cause the excitation of this tissue. And much lower for the intermediate tissues, but so it should be nearly negligible. Okay, so we have tried some basic approach, but it didn't work. So maybe let me skip it. So how to achieve this negative radiation pressure? So as mentioned, the safest approach is the safest. So it has to. If CPT is right, yeah, I don't know how it could not work, is with a synchrotron. Maybe laser plus optical isolator, but maybe not. So another relatively accessible way could be ring laser, as I've mentioned a few times. So ring laser, we enforce circulations in one direction, and it causes excitation of this target. So acting on these equations. From CPT perspective, the circulation, photon circulation is reversed. So it causes excitation of this target. So in standard perspective, it causes de-excitation of this target. Yeah, so it should act as a pump for photons, at least in theory. So it would be great to test it, but it's very difficult to get access to ring laser. They're quite costly. And finally, this synchrotron radiation, like free electron laser. So we have literally electrons going in this Wigler undulator, produce photons. From CPT perspective, they should produce photons in the opposite direction. So for example, from two-way quantum computers, you would like to put this photonic chip, for example, here. So this way, from one direction, we push photons actively there, but from the other, we actively pull photons there. Yeah, so we both on it from both directions. And so here is the last philosophical slide. As I mentioned, that present is not in agreement with CPT symmetry. We need to use eternalis. For example, in general relativity or quantum field theory, they are necessary. And there is some nice thought experiment that in theory, general relativity allows for a wormhole, which is like climbing bottle is non-orientable. So in theory, going through such wormhole, we would switch the past and future. Yeah, so it's not probably not they are probably not exist, but in theory they are allowed by general relativity. So going with rocket with one quantum computer through such wormhole, it would get change measurement into pre-measurement and preparation into post-paration. Yeah, so this is another theoretical, but in theory allowed way to get to quantum computers by taking the state preparation process to the non-orientable wormhole. Also, it would switch the two equations. Yeah, so again, so this is the question: how to switch the two equations to act with on one side from this equation and on the other with the second. So let me summarize. So there are a few ways to, in theory, which in theory should allow to reverse the state preparation process. So also the topological are very time symmetric. So literally there are paths in space-time. So maybe it's natural to reverse and or just to use reversed impulse, which was used for state preparation, or maybe if state preparation is done with low temperature, then it's the same from CPT perspective. So why use it in before, not after, or this pump-like settings. For example, here with superfluid quantum computer plus connected to the pump, or maybe with analog of pump for photons, like ring laser, maybe synchrotron radiation. So let me finish here. So I think these are quite. This is a matter of time where when two-way quantum computers will be realized. And for example, one of the consequences, we should think about better post-quantum cryptography, which is resistant for LP solver. I think is very important. And there are various ways to do it. So for example, this photonic, that we have literally laser resonators, but not only from one direction, but also the second. So we have photonic chip between couplet resonators, and from CPT perspective, we reverse this photon direction. So again, this is in theory to a quantity. Okay, thank you for the attention.
Okay, thank you so much for such an amazing talk. So now we are open for Q&A session. Mm, Are there any questions? Okay, it seems like we don't have any question at the moment. We will be uploading this video to YouTube channel, and Dr. Duda, if some participant is interested in asking the questions, how should they contact you?
So you can email me. It's easy to find me. Or in the slides, I think I have put the Discord. So this is a Discord link, and here it should be active for a week. So in any ways, you can join to our Discord with 80 persons with quantum computers.
Yes, he's quite active on Discord. Other than that, you can also find on LinkedIn. So I guess that's it. Let me stop the recording.